Welcome back for the second lecture on algorithm design. We'll talk today about divide and conquer algorithms. Remember that we're talking about algorithm design strategies with an eye towards what we've seen and looking forward towards future algorithm discussions. Today's topic, divide and conquer, comes second in the order of our four classes of algorithms. And remember that our goal here is to learn a framework of problem types that can be solved using different classes of algorithms. Last time we talked about greedy algorithms that can solve problems optimally if they obey this optimal substructure problem and they have this greedy choice property leading to an optimal algorithm. Today, divide and conquer algorithms. Divide and conquer algorithms are beautiful, oftentimes beautiful algorithms that exemplify a so-called top-down technique. And the name tells you a lot about the types of algorithms. We divide the problem first into, and if our initial problem is called S, then we divide it into two or more disjoint subsets, S1, S2, and so on. So we might divide the problem in half or into thirds or something like that. And then the conquer part is to solve each of those subproblems. And usually, though not always, this is recursive. We could replace that recursion with, a stack, but oftentimes the most natural formation of this is recursion. And we reach the base case of each subproblem when we have a constant size subproblem or something that we can solve in a fixed amount of computation. And then left, usually out of the name, is the topic of combining. So we have divide, conquer, and then combine. Oftentimes we have to do some cleanup work that after we've solved the subproblems by the conquer step, by recursion, we often have to combine the solutions that we solved as subproblems into a solution for the overall problem. And an important point in all divide and conquer approaches is that the subproblems must be disjoint. They must not overlap. If we if they overlap and we're solving under two subproblems, some overlapping portion of the problem, then we're doing the same work twice or more than twice. And this is what we call one of the four rules of recursion, the compound interest rule, as our textbook calls it, that we want to avoid doing the same work more than once. When we talk about overlapping subproblems, that's actually in the next lecture on dynamic programming. So I wanted to give you a quick set of examples on problems that we can solve or algorithms that are divide and conquer. We've seen merge sort and quick sort are both divide and conquer algorithms where we split an array into two pieces and then recursively sort those two pieces, and then we might combine them as we come back up the recursion. We'll talk today about two algorithms, Karatsuba's algorithm and Strassen's algorithm, for multiplying large numbers and large matrices. We'll talk about quick select, and we won't talk much about finding the closest pair of points today, but I'll just mention it here and say, if you had a two-dimensional set of points and you wanted to find what the closest pair of those points were, the naive strategy would be to look at each point and look at all of the other points and then do that for all pairs, and that would be, and the least distant pair would be the closest pair, and that would be an order n squared algorithm. But there is a somewhat complicated but elegant nonetheless algorithm for solving this problem in n log n time, and it makes heavy use of divide and conquer. So you can look that up if you're interested. Before we talk about any of these algorithms, we really have to talk about something called the Master Theorem. And this is the best way to do analysis for recursive or divide and conquer algorithms. And it looks a bit daunting. The proof is actually fairly nice. I would encourage you, if this appeals to you, to try to do the proof for the Master Theorem. We have seen in the past runtimes, T of n's, that look something like this. T of n equals some function of itself plus some other time, okay? This is a recursive definition of T of n because T of n is not just n squared or n cubed, but it's T of n is a function of T of n. It's a recursive definition of T of n. And this arises because if we have a recursive routine, it's calling itself. Now, the master theorem is a method for analyzing a lot of such algorithms that are defined recursively. And it says this: if you can write a runtime T of n in the following format: A times T of n over B plus theta of n to the k. Okay, if that's possible, it's not always possible for all problems, obviously, but if that's possible, then the master theorem gives us the solution in this table right here. And proving that is the interesting part if you're interested. And you can do that on your own. It depends on the relationship between A and B to the k. Now, let's come back to this because before we talk about these consequences, let's say what are A and B and k? Well, A is the number of subroutine recursive calls that we have. So if we're talking about merge sort takes an array and divides it in half and then calls merge sort on the lower half and calls merge sort on the upper half. 2 recursive calls. So for that case, A is 2. B is the size that we're using to divide our work. So if we started with n elements, our recursive call is of size n divided by b. Okay, so b is the constant which tells us how much we're dividing our work by. And k is the order of the polynomial of the amount of work that we have to do at this level of the recursion. Okay, so if we have to do linear work, then k would be 1. If we have to do quadratic work, then k would be 2. And when we say at this level of the recursion, we're saying in order to prepare for or post-process those recursive calls, how much work do we have to do? N to the k. Okay, and this could be as low as, I suppose this could be constant time as well. All right, so our relationship of a and b to the power k determines what the answer is. If a is greater than b to the k, then T of n is big O of n to the log base b of a, which looks fairly complicated. We'll see some of those examples today. If a is equal to b to the k, then T of n is equal to n to the k log n. And if a is less than b to the k, then T of n is equal to big O of n to the k. Okay, so let's apply this to merge sort. As I said, with merge sort, we're dividing the array in half each time. So b here is 2, okay? And a is also 2, right? That's because we're making 2 recursive calls, one on the lower, one on the greater portion. And k is 1 because we have n to the 1 here. Okay, so if we apply the master theorem, we ask the question, what is the relationship between a and b to the power k? Well, a is 2, b to the k is also 2, so we have a is equal to b to the k. So we would apply this rule, and we would say it's T of n is equal to n to the k is 1, so n log n. And we've already done the analysis for merge sort, and we know that the analysis is n log n. So the master theorem gives us in one step the analysis for merge sort. Okay. If we were to apply this, the master theorem to quicksort, we would find a similar result. Let's talk about the fast multiplication of n-digit numbers. Now, when I say n-digit numbers, I'm thinking n very large. So here we have 2 8-digit numbers, right? We have 8 digits here and 8 digits here. And we want to multiply these things together. But maybe we're talking about n of being 100-digit numbers or 1,000-digit numbers. The classic algorithm for long multiplication costs us n squared time. And that's because you do 4 times 8 is 32, carry the 3, 3 times 8 is 24, add 3 is 27, carry the 2, 2 times 8 is 16, plus 2 is 18, carry the 1, and so on. I won't do this, obviously, but we're going to multiply this number with n numbers above it, and then we're going to multiply this number with n numbers above it, and then we're going to multiply this number with n numbers above it. So there are n things that we're doing here, and each of them requires n digits up here, so that's n squared time. And that might seem like the fastest algorithm, but it's not, right? There's a divide and conquer algorithm called Karat-Sabba's algorithm, which runs in time n to the 1.59. Now, where does that 1.59 come from? You might guess it comes from the Master Theorem. How does Karat-Sabba's algorithm work? Well, it's a bit too much to talk about right now, but at a very high level, what it does is it defines this multiplication as a multiplication between four pairs of numbers. We take this portion, the first half, let's redraw that, this portion and this portion, the first and second half of this number as x1 and x2, and then we have this portion and this portion, and we'll call these y1 and y2, and we know that the answer that we want is essentially x1 times some multiplication, which is a factor of, in this case, 10,000. We'll call that m, plus x2 times y1 times m plus y2. And don't worry about the details here. I'm just writing this down as I'm rewriting this in a different form. In order to do this multiplication, I have to multiply this term times this term and times this term. And then I have to multiply this term times this term and this term. So in total, I have 4 multiplications to do here. Karat-Sabba's algorithm shows how to rewrite this problem, reconfigure it actually, to do that all those multiplications, but with only 3, with more additions and subtractions. Okay, and so what it does is it calls 3 multiplications, divide and conquer. So we divide the problem into basically these halves, right? This portion and this portion and this portion and this portion. We're dividing each number in half and then multiplying pairs of those numbers. And we're doing that 3 times. So we have 3 multiplications, but not 4. And that's the speed up. And B is 2 because each time we're dividing in half the amount of digits that we have remaining. And it turns out that the K that we're dealing with here is 1. Okay. And so what do we have? We have A is greater than B to the K. So when we apply the Master Theorem, we get T of n equals n to the log base B of A, log base 2 of 3. Well, log base 2 of 3 is approximately 1.59. So if you have 2 very large numbers to multiply together, you can do it faster than the classic algorithm you learned in grade school using this algorithm, and it uses divide and conquer. A similar problem is the multiplication of n by n matrices. If I have an n by n matrix here, n rows and n columns, and I have another n by n matrix here, the result is also an n by n matrix. And the question is, how quickly could I compute this answer? Well, the classic algorithm takes n cubed time because I have to multiply this row times this column to get this value. And this row and this column, that's 1 times 1 plus 2 times 2 plus 3 times 3 plus 4 times 4. That's an order n operation. So each one of these elements cost me order n, and there are n squared of them. So clearly that's an n cubed operation. Okay, but there's a divide and conquer algorithm called Strassen's algorithm that runs in n to the 2.81. And as you might expect, it works by divide and conquer. The divide and conquer steps that we do is we divide each of these 2 matrices into quadrants, let's say. And in order to get, say, this quadrant in the answer, we have to multiply this region with this region and this region with this region, right? We have to do essentially this times this to get this. Okay, so that's, if you think about it, that's going to add up to 8 multiplications to get all of these quadrants. And I'm skipping over a lot of details here. But what Strassen showed is that instead of the 8 multiplications that you have to do of each of these quadrants times each of these quadrants, and it's not all pairs of quadrants, but you would have to naively do 8 multiplications, but he showed how to reduce that down to 7 multiplications of these subquadrants, and each of those is of size uh, essentially half as big, okay? And the k here is still 1. And again, we have a is greater than b to the k, so applying the master theorem, we get n to the log base 2 of 7, which is roughly 2.81, which is faster than n cubed. So if you have very large matrices, you can use Strasson's algorithm and divide and conquer to make it run faster. Okay. Last example I want to talk about is quick select. And this is a new algorithm. It sounds like quick sort because it is like quick sort. It's based on the same ideas as quicksort. But the problem that we're trying to solve is different. We're not trying to sort an array. What we're trying to do is get the kth largest element of the array. So our input is an array of length n and an integer k. And our question is, what is the kth largest value? So for example, suppose that this is our array down here. Suppose we ask for the first largest value. Well, the first largest value is 1, right? It's the smallest value. If I ask for the 8th largest value, that would be, I'm sorry, the the kth ordered value, let's put it that way, okay? The kth ordered value. So the least item in here is 1. The greatest item is 10. That's the k equals 1, right? And that's k equals 8. Well, you might ask yourself, how quickly could we answer this question? Before we get into the nitty-gritty of all of this and this algorithm, imagine that you just wanted to find the least or the greatest. How quickly could you do that? Well, you could scan through the entire array looking for the least, and you could find it in order n time. So let's say, you can find the min in order n time. And you can also find the max in the same way in order n time, right? But it seems like if you want to find the median element or the middle element, if they were sorted, it's more difficult, right? Because it seems like you'd have to sort it. Sorting costs you n log n. So it seems like it's not as efficient. But here's the idea behind quick select, okay? The quick select algorithm relies on the partition algorithm that we talked about in quicksort. And we take the array and we partition it into 2 segments, L and H, the low and the high. And then what do we know? Well, we know that if we've taken that array and we've partitioned it so that we've got the low and we've got the high, and this might not be an even split, right? We know that partition, we want to have roughly 50% over here and roughly 50% over here, but we know that that's not always possible. But the thing is, let's suppose that the partition dividing line is at, 100. And suppose that k equals 200. We know that based on partitioning, everything down here is less than or equal to everything up here. So after we've partitioned, and if our partition is at 100, we know that the k value that we're seeking must be somewhere in this region. Or conversely, if k was not 200, if k was, 3, then we know that we would have to search the low region because k is less than that partition. So that's the algorithm's main idea. Partition the array into 2 segments, and then recursively look in only the segment that contains the kth element. Okay, and then after if you're going to recurse on, say, the low region, then you might partition it again, and then maybe you recurse on this region, and this region, and so on, until you get to the k value that you're seeking. So the runtime for this is as follows. T of n equals T of n over 2 plus order n. Okay, well, where did these numbers come from? Well, notice that A here is 1, which I've written there. Okay, why is A 1? Because when you partition into 2 portions, you're only recursing on one of those 2. So we're only doing one recursive call. And why is it n over 2? Well, because we expect that on average, the 2 sizes of these subarrays are going to be equal. And so we're going to take roughly half as much data per subproblem. And then where does the order n come from? Well, that order n is the cost of that partition call on an n-length array. So we have a is 1, b is 2, k is the power of n is 1. So a is less than b to the k, which we haven't seen before. So we would have t of n equals big O of n to the k, which is n, which is linear. Now remember, we could find the minimum element in linear time. We can find the maximum element of it in linear time. But what quick select allows us to do is find any kth largest element in linear time. It's a little bit more complicated, but we can do it. It's a very nice, elegant algorithm. Okay, so a recap on divide and conquer algorithms. It's a top-down technique. We think about big problems and how to divide them into subproblems and solve those recursively and then combine their solutions. And the really important thing here is when we divide, we're dividing them into disjoint, non-overlapping subproblems. Because if they're overlapping, then we're breaking one of our rules of recursion. And then to remember that we can always, or almost always, often apply the Master Theorem for divide and conquer algorithms, where if we can state the runtime recursively as this, then we can look at the values of a and b and which one's larger, a or b to the k, or if they're equal, and then we just pull out the answer from the Master Theorem. And again, I would encourage you to try to prove this. The method of proof is simply to take a problem of size n and then think about if you have a subproblems, say 3, and you have n over b in each of these, right? And there are a, say 3, or however many subproblems, and then each of those get broken up into n over b squared, right? And then the question is, how do you prove how much work you do at each of these? Well, you have n to the k work here, and you have n over b to the k work here, and you have n over b squared to the k work here, and so on. And so proving that the sum of all of these things is one of these. And it looks a little nasty. It's actually quite elegant and fun to prove. So I hope you give that a try. So next lecture, we'll talk about dynamic programming.